Hello and welcome. My name is Prasad Venkatacha. I'm a solutions director focused on the database analytics at Pliops. In this session, I'm going to be talking through how do we empower real-time decision making for large-scale data set with SSD-like cost economics. So the contents of today's presentation can include the need for real-time data, and the in-memory applications that supporting the real-time data, and how do you extend the data sets from in-memory into the flash storage, and making sure that all the performance testing and the analysis we carried out to support that narrative, and the cost economics. How do we help to minimize the cost when we scale the data set from in-memory to flash storage for facilitating real-time analytics. So by year 2025, an user will have 4,909 digital interactions. This is going to increase from 1,450 as of year 2022 to 4,909 digital interactions. So this could be you're starting off your day morning, checking how is your stock is performing in the E-Trade, to checking your priority mails in the Outlook, to checking your all the social feed from Twitter, LinkedIn, and Facebook, and you're booking your Uber drive to office while listening to Apple Music and placing things purchasing on the Amazon. And the evening time, you want to relax, with streaming apps from Netflix, Hulu, or any of the gamings from Activision and Blizzard. So all these digital interactions is profoundly changing the shape of the business today and impacting companies in every industry. And according to IDC, 30% of the data will be real time by 2025. So how does the enterprises starts looking into building the apps and their apps, whether it is for B2C or B2B, for respond to the real world demands. So for highly interactive applications, the responsiveness is key to engaging customer experience. All modern digital interaction has to be seamless. B2B or B2C users expect a real-time responses to their requests and transactions. And for business apps, user responsiveness is a fundamental factor that determines the customer interest, behavior, retention, and loyalty. For example, let's pick an app which is, the response time of that app is, let's say, to begin with at 0.1 second. And the user behavior would be, is a very happy user because it's getting the instant results. And the same app with the increased data set or users increases the response time from 0.1 second to 1 second. Then here, the users think that this app is literally working to fetch the data, but the flow of thought, what he wants to, how do you want to use the app gets interrupted. Let's now, if the response time increases from 1 second to 10 seconds, then user starts doing multitasking. We feel that this app is not responsive enough. Let me start using that time to do other important things. Then users start multitasking. Then it also implies that you lost the attention span of the user for your business app. And for the far extreme case, if this increases to greater than 10 seconds, the user will say goodbye, this app is not working for me. It's a complete waste of my time. It's, you'll stop using this app and say goodbye to this app. This causes a significant customer churn. And if you're investing a lot of investment into customer acquisition cost, it's not only loss of revenue, but it is also a significant cost impacts because you invested a lot into customer acquisition cost and you are losing the customer on the other hand. So let's understand what's the technology that determines the responsiveness of an application. So typically a customer is facing application will have an in-memory cache, which stores the frequently accessed data from the app and this will be in few gigabytes to hundreds of gigabytes to a few terabytes. And then the majority of the data set is fetched from the stored in the several hundred terabytes stored in the backend database. This could be relational database or NoSQL database. So as the query pattern increases or changes and the number of users increases, or the in-memory cache hits the storage limits, then the responsiveness from the data set, which is not stored in-memory cache, it has to go and fetch it from the backend database. That's how the responsiveness of the application gets impacted. So as I was highlighting in the previous chart, that causes user churn, a loss of revenue, and some of the applications has an SLA compliance in terms of the responsiveness, and there is a huge SLA penalties incurs as part of it. And this is also true for a business intelligence application where the business execs, the properly, the regular business reports, we frequently using business reports is stored in the in-memory cache, and also it could be also using a fresh and latest and greatest data is used in the in-memory cache, which is could be a 1 week worth of business insights, and all the multi-year business insights is stored in the backend database. Let's imagine like you had a product launch, and based on the good demographic study you've done a product launch, and the business execs wants to take a decision on based on the 1 week of business, the sales data, and to introduce some promotions or any of those things. But this could be a false trigger because the multi-year business data tells has a lot of other information which tells this is just a seasonal fluctuation, and introducing any of the additional promotions, discounts will impact the revenue down the line, like the user purchase patterns will change. So this could be, that will be severely impact how the business executives wants to take the decision. And secondly, as I said, like the multi-year business data is in the backend database, there'll be a lot of hidden treasure of insights that will tell, like, what are the opportunities for upsell and cross-sell. Those information will be lost. It's not provided to the business executive to think about, right? So there is an opportunity loss as well. So both of these things are hitting the storage limits. Now, how do you scale a cache which is designed to help to scale an application, right? The scaling in app could be, one is scaling up the caching instance from small, medium, large by increasing the memory, increasing the CPU bin of the caching, right? That is a scaling up. Or you can go scale out, put an identical caching instance from server 1, server 2, server 3, server 4. Right? Both of these things, methods, has got a cost implications, right? So how do you think about another approach which will help to simplify my cost? Is there another method? Let's find out. So there are several in-memory database applications which will help, which could be a traditional relational databases, starting from SQL Server in-memory, Hackathon, Oracle in-memory. They do have the timestamp database, SAP HANA built from the ground up for the everything in-memory with a columnar storage in-memory. And the NoSQL Redis in-memory, one of the popular NoSQL database. And also you can use a MySQL and MongoDB with the in-memory storage engine. So for purpose of today's presentation, I'll be focusing more on the Redis in-memory, while we're doing an extensive work on how do we extend data set from in-memory to flash and the SQL Server, but I will focus this on the Redis for now. So we use the Redis recommended MemTier benchmark with the 3 different test scenarios. One is running the Redis on the DRAM, and the second is the Redis on flash, which is a Redis on flash is an identical 100% code compliant with the Redis on DRAM software. and it incorporates the same functionality features, everything, command set, everything. And the here Redis and Flash, here the data set, I mean, the Redis and Flash uses a RocksDB to communicate all the data that is coming from the traffic coming from the Redis and Flash to writing it in SSD. And the far right, Redis and Flash with an XDP. Here, instead of the RocksDB, we have the Pliops RocksDB API. This is 100% RocksDB API compliant. And this takes care of providing all the data from the Redis and writing into the SSD. So this is tailored, I mean, this is customized to suit to one of the customer requirement. Their objective was to use this for a 4K object size, and they wanted this to be a throughput optimized, and while providing a little bit of an SLA requirement, tolerance requirement. And the data size, their objective was to how do we extend the data set from in-memory to this while minimizing all the, while minimizing the latency impacts and also improving the throughput of this. When we carried out this experiment, here is the performance results we obtained. As you see here, we tested this from various Redis cache hit ratio from beginning at 10%. Redis on Flash without XDP performs really not delivering a higher not delivering a significant performance boost. But the same thing with Redis on Flash with XDP, we drive that with a 10% hit ratio for 10% hit ratio, 60x performance boost. And as we tested for various DRAM hit ratios, even at 50-50, at we provide a 7x performance boost. This 50% hit ratio, that means 50% of the data is coming from the DRAM here, which is already stored in the, and 50% of it, that is almost like 1.5 terabyte of data that's coming from the Flash. We provide a 7x performance advantage. And the same thing if we increase this into even up to the far right at 95%, where is only 5% of the data coming from the of the 3 terabyte data set. Even for that, we provide a 2x performance boost, and the XDP provides a 2x performance boost. And this numbers is close to, especially on the 95%, is close to the Redis on DRAM performance, which is only 300 GB of data set, whereas on Redis on Flash with XDP is at 3 terabyte of data, which is a 10x more data, and delivering at a close to identical performance of that of the DRAM. Performance come from the performance. Let's look into the latency aspect. Here, as you see, for both for the get and set operations, the 4 nines latency, that is 99.99% of the user request is being served at a consistent latency for both the get and set operations close to the DRAM. The objective is like, as you increase the data set from from a 300 GB to 3 terabyte, our goal was to make sure we deliver, the XDP should deliver close to a consistent latency across the DRAM hit ratios. And whereas on the same thing, the Redis and Flash without an XDP environment, you see a significant spikes at 50%, 85%, 95%. That has got a so that implies that as the data set grows, there is a performance impact in the RocksDB environment. To understand why the RocksDB behaves this way, let's see the architecture. Though the RocksDB is designed to enable to provide a faster performance for the SSD or a flash storage devices, but the problem here is like the way that it is being structured. It uses the log structured merge tree algorithm data structure, and here the writes is coming through all the writes that is coming through from the Redis application. It goes through the mem table, which is a in-memory data structure, and when the mem table is full, it flashes the content. And here it uses the the different levels of the storage pattern, where level 1, level 0, to level 3. As the data gets filled, then it navigates, push that data to level 1, level 2, and level 3. So these SSD tables, which is a sorted storage, the key value storage tables, has got it's immutable, and so now to process any of the deletion of keys or anything, then the compaction process has to kick in. So this is a huge implications on the write performance. So that is where the RocksDB suffers a performance performance challenges, right? And this is precisely what XDP, the Pliops XDP addresses it. As you see in this chart, based on, we saw that previous results, everything were focused on at the Redis layer, performance and latency. And we also wanted to show what is happening at the data storage engine, right? So here, what you see on the chart here is the RocksDB, showing delivering a 22.9K IO operations with a deviation. That's another important thing, the standard deviation of 31.8%. So every time the compaction process kicks in, there's a huge spikes or variation in the performance. Whereas the same thing with the Pliops enabled environment, which uses a better version or enhanced version of the RocksDB API, right? We provide a 7x performance boost. We improve the IO operations from 22.9K to 150K operations. And as you notice here, the standard deviation is kept to very minimal, to 2.3% compared to what RocksDB does at 31.8%. So this is another way to understand, so this is one at the application level, second at the storage engine level. The data storage engines are being, like RocksDB, there is several other data storage engines like InnoDB, WireTiger for MongoDB, and MySam, XtraDB. So there is several storage engines are being used for several applications. Some of the drawbacks here is like they have incurs additional CPU overhead to process all the data, just like what we are seeing in the RocksDB. The compaction is impacting, right? And the same thing, there is also IO amplification that is causing the performance impact. And if at the storage management layer, whether you're using a DAS, all-flash, or HDS, software-defined storage, there is a CPU overhead that causes because of the data shaping, data protection that you want to provide from RAID 5, erasure coding, and this, or replication, there is a CPU overhead. And also, if there is anything converting from a random data to sequential data through sequentialization, there is a capacity and a CPU overhead. There is also underneath at the SSD level, there is some amount of overhead for over provisioning, and you have to factor in the DRAM and some of the processor that is incurred. So let's looking at these. There's several different applications, not only on the Redis. For example, if you're using an SSD, TLC SSD, for a smaller the user digital transaction that very initially talked about, this is like a user making a comment on his social feed, like, this could be as small as 100 bytes of IO. And when it go and rise to the TLC, which is a 4K SSD, it incurs a significant IO to 40x IO amplification. Whereas on the same thing with the QLC, it incurs a 64x IO amplification. The QLC is good for high density, low cost, but imagine incurring a significant right? So all these things will have implications. The IO amplification impacts the CPU. There is a memory overhead and a network overhead on top of this. So Pliops XDP will help to elevate some of these challenges in terms of collapsing multiple layers of CPU overhead from the storage engine to storage management to this, and reduces all the IO amplification impacts and keeps it to the very theoretical levels, which is where the desired levels should be, so that you get a maximum performance. And it is universally applicable to several applications, not only the one I talked about on the Redis. Now switching back onto the Redis, in-memory application using extending into loss settings on flash, Redis on DRAM, performance and latency you get the best, but you can't get you can't address the data set. Redis on flash, you get address a large data set, but you miss out on the performance and latency. Redis on flash with XDP provides the performance, latency, and data set, and we'll take care of, also will be no impact onto the, we keep the theoretical levels of the read amplification, write amplification. Let's look into the, this is a cost-effective way of scaling a cache. So thereby you can seamlessly expand the in-memory cache to large data set, or you can even think of unifying the cache and the backend database into one large entity. And this way it enables to look into for a multi-year business insights rather than storing into a smaller data set. So now look into the cost effect, you can look this from a macro level, from a data center level, reducing the data center footprint, server and everything, or looking at a application specific to the micro level, high performance, high capacity, high performance, reducing the dollar per terabyte, dollar per IOPS. You can approach either direction. So one way to illustrate, take advantage of these things, 7x higher performance, 4x lower latency, what we have seen in the previous chart, will be translated to in a 22 instance in a single rack, and delivering at a 145K IOPS per server with 79 milliseconds. The same thing set up running at 956K IOPS, that is 7x higher performance boost, 19.9 millisecond, 4x lower latency, and TCO per IOPS is reduced by 86%. Other way to look at that benefit is if you want to looking at if you have a Redis in-memory application, this you can get with the Redis on flash with XDP, Pliops XDP environment. You can get a 13x higher capacity for a 13x higher capacity for all the economically scaling your caching, and this reduces the TCO savings by 92% for terabyte of Redis caching. And this you can extend from weekly to months of business insight. And this is an approach you can think about for consolidating from a 22 rack servers into 3 rack servers, and reduces the 84% TCO savings. In a conclusion, you can extend from the data sets from a gigabytes to several terabytes using the Redis on flash and Pliops, and achieve all the DRAM-like performance with SSD-like economics and low variance in the performance, and it's completely resonant to all the hit ratios. Thank you for taking time to go through my presentation. Please share your feedback and rate my presentation. Looking forward to your feedback. Thank you.